To be recognized as and among the great, have the data, do the analytics, and implement it through logistics. Ladies and gentlemen, welcome to the presentation of the University of Belgrade solution. The team comes from the Faculty of Organizational Sciences, and the members are Dragoljub, an undergraduate IT student, Jakov, a master IT student, and Andriana, Nemanja, and myself, Darko, all business analytics master students. Now that the team has been introduced, a short agenda insight follows. At the very beginning, we will be talking about the problem statement, with the main idea of coming closer with the data that we have used in the process of the demand forecasting. The demand forecasting process is the starting point and the input for a route optimization that provided us with some solution we like to call our own and that we are here to analyze and explain. At the very end, a short conclusion will be given and the future research that we find interesting. In order to, optimally solve any problem, one must have a well-based premises. We have decided for 3 of them that we find the most and the best explaining. The number 1 is network elements, where plants and dealers could be explained as the points of demand and the production, while the easiest way to explain VDCs is as the cross-dock system. The transportation mode is the second one. We have introduced truck, railroad, and autonomous vehicles with a special accent on AVs for their cost minimization role as well as innovative power. The third, last but not least, is the demand as the driver of this whole system. Now, the first element of the data we would like to discuss is the raw data and the explaining of it. Let's start with network elements. We had 4 plants and 39 dealers, VDCs, out of which 33 were active ones. The logic follows for the dealers, where we had roughly 21,000 of them and roughly 9,000 of them being active. The transportation modes previously mentioned, all of them were in use, with 79.3% being fully loaded and 96% of them being direct plants dealer, or the ones with 3 legs. The time interval and the data of it, the years of 2001, 2003, and 2010 and 15 were excluded due to their data inconsistency, as shown in the lower part of this graph. The full data set was provided for years of 2011 to 2014, and it will be better explained by my colleague Dragoljub. Please proceed.
In the period of 2011 to 2014, the second part of data we want to present is cost, more precisely logistics cost. The idea behind the given matrix is that we have 3 transportation modes and task of choosing one of them. We define optimal solution in every situation using 2 variables, number of vehicles and distance in miles. First, we will compare truck to rail. Their costs are as shown. Sorry. They are consist of 2 parts, transportation cost and penalty cost. The results of this comparison are shown in the figure. Relevant number of vehicles is 20 because it's smallest common multiply of their capacities. For example, for 9 vehicles and distance less than 2400 miles, truck is better, otherwise rail is better. It's visible that on 11 vehicle is turning point because we will need another truck for that extra vehicle, which will double transportation costs. Now we will compare track to AV. In this comparative analysis, we excluded penalty costs because they are the same due to same transportation speed AV and truck have. The logic is follow. In this segment, AV is better, otherwise it's truck. According to the problem statement, we formulated model characteristics that are desirable. First, can handle large number of vehicles. Second, plants can ship to any VDC. Third, dealers are assigned to closest VDC. With those characteristics, network is modeled as undirected graph shown in the figure. The VDCs are represented as circles. The bigger the circle, the more dealers are assigned to it. With this method, 39 clusters are created, each with 1 VDC, and on average more than 500 dealers assigned to it. Now with data segment as explained, my colleague Jakov will continue with demand forecasting.
Thank you.
Demand from each VDC to each plant was forecasted on a daily and a monthly basis. New data sets were created, and plant VDC pairs are made upon previous clusterization. The demand was aggregated according to those two time units. Many dummy variables are created where needed, and months and days are extracted from dates. Several widely known methods for forecasting were tested against the dataset, such as Holt winters and vector regression. Later on, it was decided to use a neural network approach, more precisely long short-term memory recurrent neural network. Basic and complex models were introduced, where in the complex one, a recurrent network was combined with convolutional network, as it was proposed in the literature that had been analyzed. Symmetric mean absolute percentage error, or shortly SMAPE, was used to measure the quality of different forecasting approaches, and it showed recurrent network to be better than above mentioned methods. SMAPE measures the difference between a forecasted and actual demand with respect to their average. Distribution of error for monthly and on a monthly and daily basis for both basic and complex model is presented here for randomly selected pair plant VDC. As it was supposed, the supposed error tend to be lower on a monthly basis, while overall error is not as high as we expected it to be, mostly because of correlation between historic data set and given data set. On the next few slides, we see the difference between forecasted and actual demand. Black line presents the actual demand. This is forecast for first 6 days of our set, for 30 days for forecast, and 90 days forecast. It was concluded that basic model is better at catching trends and seasonality, and how this information is used will be explained later on. I would ask my colleague Adriana to proceed with routing optimization.
Okay, by using route optimization, which tried to reduce total costs of running the network, including logistic and penalty cost, by reducing lead time between order and delivery time. The shipment of vehicles from plant to dealer is divided into two stages. First, from plant to VDC assigned to dealer, called final VDC, and from final VDC to dealer. For the first stage, there were two decisions to make. First, we make decision about transportation mode in VDC or in plant, which we use criteria which compares truck and rail costs, similarly for AV and truck costs, based on number of vehicles and route length. Second decision is about processing the vehicles. To wait or not is based on monthly forecasting. If there are not enough vehicles for full load on truck or a rail, we make decision whether to wait or not if higher number of orders is expected, again based on monthly forecasting. For the second part, from final VDC to dealer, we implemented two strategies for solving milk run problem based on traveling salesman problem and vehicle routing problem. In both strategies, we request the truck must return to starting VDC, which leads to higher costs but reflects more real situation. For TSP approach, vehicles are grouped and problem is solved on each group, which is not necessary for VRP because it generated more routes with specified capacities. Vehicles that are supplied via single VDC are grouped in clusters of maximum 10 by their relative position given by the angle of their polar coordinates. For every group, we used heuristic based on genetic algorithm to find feasible route. On the other hand, when problem is considered as vehicle routing problem, we used enhanced savings algorithm. What is the main idea? The main idea is to use enhanced routes merging and dynamically calculate corresponding savings during the iterations. S has polynomial complexity, and to improve S efficiency, randomization with multi-start is used. In our preliminary experiments, we found out that VRP has bigger fixed costs and lower utilization of the truck. So, for example, with one small example with 73 orders, where many of dealers ordered exactly 6 vehicles, there were 12 shipments if we use VRP and only 8 if we use TSP. So, for that reason, we've decided to use TSP, and obtained results will be covered by my colleague Nemanja.
Okay, Before I go to the solution analysis, I would like to say that we use Python programming language for generating our solution. In the end, we generated two solutions. One of them was with introducing the concept of autonomous vehicles. We will call it solution with AV and solution without AV. It took a total 2.5 thousand minutes to generate for the first one and 4,000 minutes for generate the second one. But have in mind, this was the running time for the whole data set. If we say that recommend decision frequency is 3 days, it would take approximately 10 minutes for the first one and 50 minutes for the second one solution to be generated. Also, we use other tools such as SQL Server and Tableau for data analyze and graph visualization that you will see on next slides. The first graph shows us the comparison between these two solutions. We can see that overall performance of solution with AV is better, having the lower cost for logistic costs and the lead time cost. The only segment where solution without AV was better was the VDC cost. Reason because of it, we have higher overflow of vehicles in the warehouse. The next slide shows us the percentage comparison of these two solutions, and we divided the logistic costs in the shipment cost from the plant to the VDC and the milk run costs. We can see that milk run cost is lower in solution with AV. Reason because of that, we don't always wait for the full shipment, but we ship directly to the dealer. This graph shows us the comparison between reference data set and our two solutions. We have bigger average cost, but as Adriana told, we introduced some costs that were not given in the reference data set as returning the truck from last dealer to the shipping point. For the other costs, VDC and the lead time costs, they are pretty much on the same level. Lead time analysis. Lead time is an important indicator in automotive industry. Shorter lead time means that a company can fulfill demand quicker for their customer. And in reference data set, median was 12 days, wherein both of our solution outperformed the reference data set with 6 days of median lead time. Now the question is, what can we do to lower our costs? One of them is parking system. Parking system that was given in the written statement implies that vehicles are parked parallel next to each other. What we proposed is to install the lifters that can stock two level of vehicles. This change can increase original VDC capacity to 60% with only minor changes. What else could be done with reducing the costs? And the conclusion will be given by my colleague Jakub.
Thank you, Nemanja. You heard about parking optimization, while another recommendation advises to take traffic congestion costs in consideration. A report of INRIX, a respected company for traffic analysis, states US congestion costs to be $87 billion and 97 hours wasted per driver. We believe that our figures could be maybe even better with proper usage of traffic data, and therefore we would recommend using Google Traffic API, since its vast usage makes it agile and up to date. At the end, I would like to conclude that logistic cost analysis gave clear recommendations when and whether to use AVs, trucks, and trains. Demand was forecasted, that later helped in route optimization part, where two modes have been examined. And all that led both of our solutions to outperform a reference data set in lead time, and to conclude actually that a solution with AVs had significantly lower costs compared to the non-AV solution. So, ladies and gentlemen, thank you for your attention. I would like to say thanks to our professors from Faculty of Organization and Sciences, University of Belgrade. And I would like to say thanks to my dear colleagues. Thanks.